to unified conferencing.
Coffee soon? Anybody want a shot? You got to put a thing in there. Yeah. There you go. In there. All right, it's about time. So I got back from the ACS yesterday, and I'm a little under the weather. So if my voice gives out, forgive me. So today we're going to start talking about how to actually make stuff instead of all the incessant reactivity and substitution we talked about during the first week of lectures. So first, a little bit of strategic discussion. When do you make stuff versus when do you buy stuff? The trend is definitely like I show here. And it actually tracks well, again, with aromaticity. So the more aromatic the thing is, not surprisingly, the more likely you are to substitute it. And if you need a reminder of that, how often do you make your benzene rings? Right, so same thing. You will make pyridines. We will talk about that. It's really useful to know how to make them, but you're generally, as we talked about last time with the Lilly and Pfizer folks, generally going to buy your pyridines. But then as you start moving to the more five-membered ring character, as we'll talk about today, the pyrrole ring, you'll find there's more synthesis going on. And when you start going to six-member rings with more and more nitrogens, a lot of synthesis going on. It's really important to know how to make, for instance, purines, because those are like the prototypical versions of fused heterocycles of the type that you see often in modern medicinal chemistry. And then as you start benzanulating, it also becomes important because if you think about it, you've got a benzene ring connected to a heteroaromatic ring, and which one is more aromatic? Obviously the aromatic ring. So you're going to have to break up the other side. So all of this is rather intuitive, I think, but worth remembering when you're confronted with a problem, especially when you're confronted with the problem of fused heterocycles. So luckily, was it Patrick who posted that problem, which is really way too advanced for today's lecture. But just based on this, we can muddle our way through that later on. You'll have to wait till the end. Okay, so how do you make heterocycles? Well, there's basically just 4 ways of making these rings. And in a very global, diluted sense, you've got the nucleophile-electrophile pair that are connected to the molecule in either polarity of that, or you've got some sort of bis nucleophile or bis electrophile that is then attacked or is doing the attacking. And that's it. Those are the only 4 ways you're going to see to make heterocycles. Often it's driven by thermodynamics, so you'll often lose water or some driving force to aromaticity, and that's what drives ring synthesis. The nucleophiles are usually some heteroatom, and the electrophiles are some sort of electrofuge, whether it's a electron-deficient olefin or a carbonyl or an imine or a nitrile. Those are basically the categories. Okay, we'll get into this sort of box of strategery later on when we talk about all the ways of making pyrols, but these are some of the rules that we'll talk about in just a moment. Now, the most important thing to think about when you think about a pyrrole or a furan or any type of 5-membered ring system with 1 heteroatom is almost always you can break it down to the 1,4-dicarbonyl. In every pyrrole, at its heart, there's usually a 1,4-dicarbonyl that's hidden in it. And that goes for furans, too. So problem of the day number 1 is a very simple one. It just asks you to go into a free-form brainstorming session on equivalence to 1,4-dicarbonyl. So maybe what do you say, Tucker? You want to help us out? And you can draw on the iPad, or you can call out your thoughts. There's probably several hundred answers to this question.
Kind of like starting materials that aren't already pyroles.
Starting materials are not, but we're not going to degrade the pyrrole down. What we want is a synthetic, what we would want to call them synthons. So they can be in the wrong oxidation state. They can be in the correct oxidation state. They can be something that you can massage into the 1,4-dicarbonyl. Basically, they are, what would you say are precursors to this type of thing that contain the 4 carbons of the dicarbonyl. So we don't want to make it, don't give me a Stetter disconnection with a methylvinyl ketone and aldehyde and say, I'll make it that way. I'm talking about 4 carbon chains that can be derivatized and somehow turned into the right oxidation state of a 1,4-dicarbonyl. What would you say are good equivalents of it? Almost anything you say we can turn into 1,4-dicarbonyl. Let's see what he's going to draw out here. All right, let's draw that one. That looks pretty good. There's hundreds of them. So we're going to stay here until 11 o'clock today, and Tucker's going to draw them all out. And the rest of this you do at home. Now, just give us maybe one more, and then we'll sort of wax on that theme. This is great. So what else can you do?
Just the diacetyl.
Love it. And I love the shirt. Edison was a thief. A dirty, dirty old man that we should not celebrate. Tesla, on the other hand, if you see a shirt, was...
Edison stole everything from Barbus, right?
What's that? All right, that we're not going to go into. So, how about butadiene? How about... that's fine too. How about... that's okay. Now, when I say equivalent, I mean you can use an oxidant if you want to. It doesn't have to be the exact same oxidation state. You're just fine doing that. Butadiene, you probably learned in organometallics how to convert that into a 1,4-dicarbonyl, right? Some sort of Vacker-like conditions would eventually give you the right thing. So you get the idea. Basically, you can start inventing 1,4-dicarbonyl equivalents, and that will give you a precursor to a pyrrole, or tomorrow you'll see furan as well. And that is a good inroad towards the basic methods for making pyrroles. There are a lot. If you want to look in the book, we'll page through it later on, but there are a lot of methods for making pyrroles that we do not cover in the class, just because some of them are rather boutique methods. And what I tried to do here was show you the 5 most popular ways of doing it, because the other ones can largely be derived from a deep understanding of the 5 canonical pyrrole syntheses, many of which rely upon generation of a 1,4-dicarbonyl, and that's the point of problem with it number 1. So let's take a look at, of these 5, I think 3 of them are going to be basically straight out of the 1,4-dicarbonyl playbook. The first one is called the Noir. So the Noir reaction, it's the oldest way of making pyrroles, involves taking an alpha-aminocarbonyl and mixing it up with a beta-keto ester. And I guess what I need help with here is understanding the regiochemical outcome of the reaction. So we do have a pyrrole team, luckily, to aid me through this class. And yeah, the maxes.
So the first condensed amine on this bicarbonyl adjacent to R3.
Now what do I do?
And then just think aldol with the amine. So I guess that probably is the amine.
Yeah.
Just the aldol into the carbonyl adjacent to R1.
So once you have this thing in hand, that you just tautomerize, and there's been a lot of mechanistic studies on the Noir, a lot of debate how it works, because people are trifling over what I would call degeneracy. So the principle of degeneracy, and you see it a lot in heterocyclic ring system synthesis, is that you have 20 different pathways. All of them lead you to the same product. That's a good indication that you're dealing with a thermodynamic situation. So many people have been trifling over the mechanism, and most people think at this point that what is required is some sort of protonation of that ketone for this to be accelerated. In any event, you can draw whatever mechanism you want. Aldol is fine, tautomerize, close, and the product of that now I use E a lot to act as an abbreviation for ester, but you can also view it as electron withdrawing group. So if there was a sulfone there or a nitrile there, E would also be sort of a placeholder for that. Now, a little spin-off of this is called the Gewald. And, you know, we're going to see Gewald again a lot. We're going to see it when we talk about thiophenes. And Gewald-like maneuvers often lead to amino heterocycles. So how does this one work? We've got the, what do you say there, Max 2?
That's the dinitrile.
So malonyl comes in. And now what do you want to do? Deprotonate the, okay, let's deprotonate the methyl. Then what do we do? If we deprotonate the methyl, where is that going to get us? Let's count. So, what's that? Nowhere. 1 to 1, 2, 3, 4, 5. I mean, we could close there, but that's not even the most acidic position. That's the first problem. And the second problem is it doesn't look like it's going to give us something very good. Aha! What if? And then let's see. What if we deprotonate here and add in there? After tautomerization, aromatization, you get out that. And then these are basic conditions, and N-acetylpyrols, not so stable. So that's just going to fall off in C2 to give you that. Now here's the thing that if you remember this, you're going to get tons of problems of the days correct for the rest of the class. When you see a carbon like that, think nitrile. See if you can remember that. We're going to see it 10,000 more times, over and over again, in so many different contexts. Bless you. Okay, let's take a look at the next one. This is also a really old one, the Palnor. And the Palnor is pretty intuitive. It's straight out of the 1,4-dicarbonyl handbook. So you just take your 1,4-dicarbonyl that you made through any way you like. You can look at problem of the day and pick your favorite way of getting a 1,4-dicarbonyl or the equivalent, and then just adding in an amine, and out pops your pyrrole. If you have an R on your amine, then the R goes on the amine, obviously. Questions on Palnor? Yeah. So, no.
I'm just going to ask you.
Okay. How about the Hansch? This is the Hansch pyrrole synthesis, but there is also a Hansch synthesis of pyridines we'll talk about later. So the Hansch is an interesting one that involves, again, a beta ketoester, with this time a condensation with an alpha haloketone. And in C2, the alpha haloketone and the beta ketoester are mixed in a different order. So you can add them all together, or you can add one and then the other, and then followed by the amine. And often you can get different regiochemical distributions based on the way you do the reaction. For example, if you take the amine and add it to both of the starting materials, or an alternative to this is doing the Hansch under rigorously anhydrous conditions, you get one set of products. So in the example shown here, what do you suspect is going to happen? Or what do you think the product is going to be? Tanner, any guesses?
So probably the amine attacks the ketone next to R2 first.
So the amine attacks the ketone.
Oh, that's so weird.
So let's imagine the clue is that the amine can be added after you add both the starting materials together.
Oh,
So if I just add these starting materials together and forget about that amine, what do you think is going to happen?
The second building block will attack the bromide.
And then
The amine comes in.
I got my 1,4-dicarbonyl. And I'm happily a pyro. Hey, Floridians. On the other hand, if we premix the amine and the beta-dicarbonyl, and then add in our alpha halo electrophile, what do you think is going to happen here? Remember, the methylamine smells like dead fish. It comes as a 40% solution in water. And you add it to the dicarbonyl. Thoughts from Florida?
First.
Sorry?
Adds to the amine. Or
Adds to...
You said condensed.
Oh, condensed. Great. Okay. Giving us that. And then we add our alpha halo compound. Now what does that do, Florida?
could displace chloride.
What does the displacing?
The nitrogen anion.
Perfect. And then closure happens, aromatization, and notice here we get the opposite regiochemical outcome.
You lost one of your estimates in the 3 position on the first one.
Did I lose something? Where did I lose, Saul?
Product on the top line should have 2 E's.
Oh.
2 and 3 position, or 4 and 5 position.
Yeah, thanks. Great, thank you.
Closer.
If you did in a different order, it would have been correct.
Sorry?
If you did in a different order, the enemy first, it would have been still correct.
If we would have done it you mean if we would have done the top one in a different order?
No, the second one, the enemy attacking through the carbon.
Yeah, that's true too. So you could imagine acylation happens and then closure at nitrogen. It might be electrophile dependent, but the way people often rationalize it is by an N attack versus C attack. In the case of the alpha chloro acetone, it's a toss-up, but I suspect that the alpha chloro is pretty reactive and does displacement first. But yeah, if you want to remember it that way too, it's fine. Any other questions? Okay, so we've covered the first 3. There's one more called the trophomove. And the reason I show the trophomove is not because I want to advocate for you to use it in its very old variant, but rather it's important for you to realize and recognize trophomove in all of its modern manifestations. There's tons of papers that come out on new pyrrole syntheses, and I'm going to save you time so you don't need to download those papers. Right? So you can just look at the table of contents abstract and say, oh, that's a modern trophomove. I don't need to download that. I'll just remember that I can do it this way. Now in the first manifestation of Trofimov, it was not very convenient. So you took KOH, DMSO, and acetylene gas, and you heat that thing up, which is obviously not the most friendly. But there's more modern ways of doing this. So in the first version of this, what happens? KOH, DMSO, super high temperature, and an oxime. What's going to be attacked? Zhang, any thoughts?
Gonna deprotonate the alcohol first.
Okay, so the oxime gets deprotonated, and then what do I do?
I guess it has to attack the acetylene.
Doesn't have many choices.
Yeah.
And then? Suggestively drawn, yes.
So the Tom rises, and I think it does 6-5. And then it condenses into the aldehyde, and then gets to the
So Trofimov is a very sneaky way of making a 1,4-dicarbonyl. How about the bottom example? Based on this logic, what do you think the product's going to be there, Saul?
I think you're going to have the oxime attack the primary bromide first, and then you're going to eliminate HBr to get to the same vinyl ether, and then do a 3-3.
And that would give you which product?
Ring-fused cyclohexyl.
But I want to know where the methyl is.
Oh. It should be in the 3 position, I think. Give me 2 seconds to draw it.
Okay, yeah, we'll give you some time to make sure.
Yeah, that's my timelines.
Everybody happy with that? So what do you think is the first thing that dibromide does when you slam it with strong base and high heat temperature?
So this could also go all the way to the alkyne.
Okay, let's imagine it goes to the alkyne. Is that let's say it goes here. Does that change your answer, Saul?
Yes,
Why?
because when you add across, you're going to go to the more stable anion, and so you're going to add the nitrogen into the more substituted position of the alkyne.
And that would put the methyl in the opposite
That would
spot.
put the methyl in the 2 position.
Even worse is when you have propine and you heat the thing up. Guess what this thing turns into?
Alkyne.
Yeah. And then the addition happens where Saul said, and if you draw out the remaining Trofimov, the product you get is that.
So what do you actually get if you mix up these?
That.
That one.
So Trofimov can be sneaky. Now, if you want a more modern version, can you invent for me a more modern? Can you just conjure up an orglet for me now?
Doing Olden reaction.
Yeah. Okay. You can publish it. Oh, it's already been published. Sorry. Okay. But yeah, that's a more modern version. You can imagine just taking a vinyl. You can take a vinyl bromide. You can take a vinyl boronic acid and do a Chan-Lam. You can take a vinyl bromide and do some Buchwald chemistry. Intercept the exact same intermediate without boiling up everything in DMSO and acetylene gas. Nobody wants to do that. And the other advantage of that is now you can start thinking about boutique reagents. Vinyls that are substituted with all sorts of things, with a halide or a boronic acid here, that you can do Chan-Lam or cross-coupling on, and you get the same thing. But I think it's more useful to learn like the 1900s method than to show you the orglet from last year, because now you can just know where it all came from. Okay, those are the first 4 methods. Now, by my calculations, there's really only 2 more that we're going to, only about 2 more we're going to talk about before we get into the boutique ones. 2 more general ones. So problem of the day number 2 is a good introduction to the next type. The next type, which involves strange creatures called isonitriles. So we need someone to help us. And Nick has valiantly volunteered. Thank you, Nick. He was like doing jumping jacks, raising his hand. That was great. Nick is right in front here. So let's see what is problem of the day number 2. Well, X and Y can be whatever you want, really. Aryl, alkyl, whatever. Don't worry about them. All right. What's Nick doing? Okay.
It's like 1/4 addition of the decryption.
Great. Let's draw it out. Super. The only little tip I'll give you here, Nick, is that we need to make this an isonitrile.
Yeah.
So if you want to erase and switch this over to NC,
Oh, yeah.
that's the sneaky part of this problem. You've got a nitrile and an isonitrile in the same one. Deliberately given here to confuse you. That's why it's problem of the day number 2. It's not just any problem. That isonitrile looks quite angry. All right. Now what do we do? Okay, looking good. Nice. Now, let's take a second there, Nick, and look at that intermediate you drew. Are we in the right oxidation state for a pyrrole? No? Why not? Like, do you have all the electrons you need to make a pyrrole?
Needs to eliminate.
It needs to eliminate, but you have the electrons you need. The electrons are there.
Oh yeah. Okay.
So he has the oxidative equivalent of pyrrole. It's there. All he has to do is shuffle things around and lose something. Now the devil's in the details on how we're going to lose everything, but Nick has definitely got the right idea. You probably just want to move it the opposite way, and if you have the isonitrile drawn a little bit differently, it would help. Aha. Yes. That's going to be a tough intermediate, but what you're really going to need, yeah. It's very close. So Nick, you got us there, basically. Let me just give you a little trick. So if you want to think about, the isonitrile can be drawn in the form of the carbene here, or another sneaky way to draw it that'll help you with all your mechanisms from now on is just draw with a plus minus at the end. And so all we need to do here is close it, and then proton transfer. Oh, not the X. X doesn't leave. It's the nitrile.
Oh,
And now look what we have. And this is just a tautomeric form of a pyrrole. So if it is a nitro instead of a nitrile, that's called the Barton-Zard. This is just a derivative of the Barton-Zard reaction. Normally, when you have an electron withdrawing group that can also serve the purpose of leaving group, those are Barton-Zard type pyrrole syntheses. But the key here is that the isonitrile and the nitrile work together to help you with the oxidation state you need. And this is what we talked about. I think we touched on this in one of the first lectures, that a key trick process chemists like to use is to buy their oxidation rather than installing it afterwards. Installing it exogenously is more expensive than buying it. So if you make a lower oxidized pyrrole, and then you need to do bubbling with air or DDQ or palladium on carbon on metric ton scale, that's not convenient. If you can buy it, it's very convenient. So a good example of this is the Van Leusen, which is basically a derivative of Barton-Zard. Let's take a look at the standard way of Van Leusen works. So you've got your pyrrole there with 3 substitutions, and it comes from this tosylated isonitrile. How do you make this thing? Sigma Aldrich. Wrong. No. Okay. Yes. You can order this from Sigma Aldrich, and then base and R3X. Any ideas where that might come from? Sorry? From the amide. And what do you want to use here to dehydrate? What is it? Sorry, Cheng? Oh, or just like POCl3, will that be okay with you? Okay. And where do we get this stuff from? We're not going to stop till we get to earth, air, water, and fire. Formaldehyde sounds good. Thanks, Nick. So we need 2 nucleophiles. One of them is kind of obvious. And the other one is tosyl sulfinate. Sulfinate, which adds into the intermediate you get to give you the sulfonate, which is tosylate. So now you know what to do if Aldrich goes out of business. So Max is shaking his head like, more useless stuff from Phil. I know. But I'm going to come back to this at the end of the class, and then everybody who thought this was stupid, you're going to be like, aha. He had a point. All right, so now we know how to make tosmic and all of its derivatives. Great. So when you take this compound and you treat it with base, and you add it to that olefin that's activated, where R2 is your electron withdrawing group. And to remember its electron withdrawing, let's make it red. So one of these has got to be an electron withdrawing group, because just like we saw in the Barton-Zard, we're going to make an anion here. And it's got to have something it can add into. So let's add it in. When we add it in, we've got our tosyl here. We've got our isonitrile. That's just standing by at the ready. And watch what happens. It's just like Barton-Zard. It's just like what Nick was doing before. Is the oxidation state right for a pyrrole? I've got all the electrons I need, don't I? All I have to do is shuffle things around a little bit. So let's do a proton transfer. Let's lose that annoying tosyl. Let it go back to the sulfonate where it came from. And this is nothing more than a pyrrole hiding. All right, so we talked about 1,4-dicarbonyl logic. We talked about semi-1,4-dicarbonyl with the Noir-like approach at the beginning. We talked about 3,3-like approaches. We'll see those when we talk about indoles. We talked about isonitrile-based ways of making pyrrole. Super useful for pyrrole, but also really, really useful for imidazole. You'll have to wait till a few weeks from now before we talk about that. There's only a couple of ways left that I want you to learn about pyrroles this morning. One of them is problem of the day number 3, a very, very useful way of making it. And in fact, this is the reaction that was used by Bruce Roth to discover Lipitor. Original discovery of Lipitor was this reaction. So we need, Steve is looking up. That must mean he wants to do problem of the day number 3. Thank you for volunteering.
So I actually have a question about the previous part.
Great. Let's talk about your question.
Is there a derivative of this kind of reaction to get substitution at what would be the 4 position?
Unfortunately, you mean no. Here?
Yeah.
No. That is one way. That is the one signaling element for Van Leusen type chemistry, because an isonitrile must be an isonitrile. And so you're not going to be able to get substitution there. But what I can tell you is that most of the great thing about this is it's fully substituted except for that position. So you can treat it with NBS and put a bromine there, Steve. And then you can Suzuki till you turn blue in the face, right? So you can put all the substitution you want there because the only one last position, it's going to eat up NBS like crazy. It's a pyrrole, loves NBS. And so that's how you'll get your last substitution if you need it. All right, let's see what he's drawing out here. Okay, he's acetylated so he's made a mixed anhydride first. Now let's see what he does. Aha! So he's going to kick it in. What's this crazy thing you've drawn, Steve? Anybody know the name of that thing? Munchnown. So this was discovered by Rolf Wiesgen in Munich. And what better name than a Munchnown? So once he deprotonates it, it will officially be a Munchnown. Now what do we do, Steve? What are you doing here? If you want, you can just annotate the structure you've got on the left.
Okay, so you have a dipole.
Okay, you got a nice dipole. That's the Munchnown. So just draw a little minus here and we'll know what you mean. All right, now what do we do with that thing?
3 plus 2 with your alkyne.
All right. Hopefully you get your regiochemistry right. Okay, looking good. Now what do we do to finish it?
Just do a retro.
Great. Thanks, Steve. This is the Wiesgen pyrrole synthesis. And it is a representative member of the ways you can do cycloadditions to make pyrroles. Another key way of making them. The Lipitor story is quite dramatic. The reason Bruce did this is because he basically had intuition that this would look a lot like the statins, the natural products that had been isolated. And when he was doing his PhD at Rochester, he was working on munchnones, and this is a reaction he knew well. So he thought, just going to make some munchnones, and these pyrroles with substituents on them look vaguely like a statin. That's it. Drug discovery was very different long ago. They don't want to do this on large scale, obviously, so they need a process route. And until recently, and this may be the way generics still make it, the way you made this was just using lecture 2. Remember we talked about Stetter? So you make the 1,4-dicarbonyl using a Stetter reaction and then just palnor it in, your amine, and that out pops out Lipitor. All right, we need a Bogarite to help us with, how about Gigi? As part of the 400 papers you had to review for the entrance exam to Dale's group, you probably vividly remember this one. So we'll give you a problem of the day number 4, which essentially starts off with, what happens here, Gigi?
Did you mix the double bond or first material?
Yeah, there's a double bond here.
So first do a 4 plus 2.
Great.
And reach a 4 plus 2 with the nitrogen. Okay.
Awesome. And eliminate methanol. Great. And we'll just put R there. And hopefully that's the same as problem that I did before. Great. Yes. All right, now I need your help there, Gigi. We're going to treat that with zinc and TFA. And somehow this thing converts itself magically into a pyrrole. Awesome. Looks great. Perfect. And then lose ammonia. Great, Gigi. Notice what Gigi did is he took this pyridazine and got us down to a 1,4-dicarbonyl. This di-substituted pyridazine is extraordinarily electron deficient. That's why the Diels-Alder works so well in the case of the tetrazine. Tetrazines are often used as explosives. They're energetics. The pyridazines are not energetics. They're found in a lot of medicines. But when you've got these two electron withdrawing groups, these things are really electron deficient. In fact, you can do another hetero-Diels-Alder if you want at higher temperature. But anyway, they don't do that here. What they do is they inject an electron, which probably injects in a 1,4 fashion, to give you something like this, which I guess is best depicted with an equilibrium arrow. And once you've got this, the weakest bond here to break, again, zinc can come to the rescue just like Gigi did, break that bond open to give you, again, a mixture of equilibrating tautomers. You saw some of them on his answer solution there. And then finally, it all funnels down to pyrrole and loses ammonia. So this is indicative of yet another way of making pyroles, which is ring contraction. So to summarize again, we have talked about the Noir, which is not quite a 1,4-dicarbonyl, but it's reminiscent of it. The Pal-Noir, the Hansch, and the Trofimov, all those are 1,4-dicarbonyl logic. We talked about all the isonitrile ways of making these, that are the Barton-Zard, the Van Leusen, the cycloaddition ways of making these, and we also talked about the ring contraction ways. And that summarizes several thousand papers that are all derivative of this. So if you want your box of synthesis strategery, here it is. Based on what we've talked about, and which we'll see in the book as well, if you've got 3 or more substituents in a pyrrole, 3,4 disubstituted or polyalkylated, you're probably going to make it from scratch. And you should consider substitution when it's 2 or 5 substituted, 2-3 substituted, or halogenated. And you can consider hybrid approaches when you can map out easy ways of making that, followed by halogenation and then cross-coupling. So we didn't go through this, but at the end of every chapter is a really useful thing that, in fact, I find myself still using in consulting sessions, is first the starburst. We've seen these before, and you'll notice sort of all the ways of making these, and some of the boutique ways we'll get into in just a moment. But also note that at the end there's this report card, which is, I mean, maybe your parents use this, but you probably don't. Remember Consumer Reports? Yeah, you guys are so young. Your parents probably, when they bought a vacuum cleaner or a microwave, they would go to Consumer Reports that doesn't take any advertising, and they would look. And the annotations that Consumer Reports uses is pretty much the same. It's circular, not a benzene ring. But that's the exact type of notation. And basically with this report card, you can go through, scrolling through the top, and just look for your substitution pattern. And let's say you've got, that kind of substitution pattern. You're like, how am I going to make this thing? Well, you can very quickly go to the one that is recommended or semi-recommended, and then just press the box, and it will go straight to the method that you want to use to make it. So for the test, you might just copy out what the substitution pattern in your notes and what the best way of putting it together could be helpful. Okay. So let's take a look at some boutique methods of making pyrroles. The first one comes, if you look at the front page of your handout, you see a lot of these natural products, some of which we're not actually able to cover, but many of them we will in the case of things like lamellarins. So there's hundreds of these little lamellarins, and there's many, many, many ways of putting them together. So I'll show you a couple of them here because they're indicative of some of the more boutique ways of making pyrroles. When you start annulating them onto larger ring systems, often the ways you make them are just a little bit different. So for instance, lamellarin O starts off with this epoxy diaryl ketone. You treat that with BF3 etherate followed by hydroxylamine. And luckily, Dongmin's going to help us with how this works. It's very lucky because I've totally forgotten, so hopefully you can help.
Yeah, so the epoxide is going to open.
Open how?
To put a positive charge in alpha to the arrow.
So we're going to have BF3 go where?
Oh, BF3 going to the oxide also.
Okay. And now what do I do?
You'll put the epoxide from the left side, which puts the positive charge out to the arrow.
Make a positive charge here?
Yeah.
And then what do you want to do with that?
And then trap it with hydroxide.
Oh, no, I'm going to do something with the BF3 etherate. It's going to turn into something, and then I'm going to dump in hydroxylamine. Thoughts there, Steve?
So after coordination, you'll do like a diatropic rearrangement. You get a hydride shift from there, and then you form a 1,3 dicarbonyl. Would that be considered diatropic rearrangement?
I think most people would view this as like a Jung reaction, where it's like just a 1,2 hydride shift. Or, a phenonium shift to get the aldehyde. And so once you get this aldehyde, then hydroxylamine adds in, and this is your prequel to isoxazole synthesis. So hydroxylamine comes in, tautomerization, and you get out a isoxazole. Which should be the product here. Now with this isoxazole in hand, we can treat this with H2 palladium. And what do you suspect that will do? What do you think is the weakest bond, just based on what we did with problemodidate number 4? Let's break the NO bond.
See the board on the bigger screen, please?
And then we've got this vanillagous amide. And the vanillagous amide can react with the acyl chloride. To give you that. And then we have got this key step with titanium and graphite. And if you need a clue, this is Furstner's approach to lamellarin O. What do you say there, Max?
Reductive carbonyl coupling.
Where to where?
Between the ester and the aryl carbon, yeah. Well, between, I guess, we're going to make 1 and 5.
So 1,5. Yes.
Yes, McMurray.
So McMurray type of closure. gives you the product. Take a look at how that maps on to lamellarin. Go to your problem, your front page handout, and look at lamellarin. It's pretty close. Let's take a look at another lamellarin synthesis. This time, this one comes from Iwao. And we need some help. How about, Elena, any thoughts here on the first step? I don't know if you can see it, it's a little small. Just give me that first step. All right, let's displace the bromine. But where? What's doing the displacing? So I have choices here, don't I? I can displace at the alpha carbon. I can displace using the oxygen in the enol form. And is there any other spot I can displace? Nitrogen. Why don't we try nitrogen first? And the general rule would be your pyridine-like nitrogens have a voracious appetite for electrophiles, more so even than things like 1,3-dicarbonyls. They love to attack these things. And so when you do that, you're going to get this isoquinolinium salt. And now I need to treat it with HCl. Any idea what the HCl is going to do? Hannah, any thoughts? What's the thing that is most acid labile in that molecule? We need a master of protecting groups.
Oh,
Mom. Let's take off the mom.
and then you're going to alkylate.
Well, there's nothing to alkylate yet. And then we're going to treat it with triethylamine. Now what happens? So you need to think, in this thermodynamic soup, what are the protons that are acidic, and what are the things that can happen that have no reversible point? Many things can happen in reverse, but there's only a few things that will happen, and then there's no going back after that. Vincent, any thoughts?
Can you deprotonate to the right of the nitrogen?
Oh, that's lovely. And now what?
That attacks the carbonyl. Yeah. And you lose water.
That is perfect. And then guess what's hanging out over here? We still have triethylamine in there. That means you probably got some phenolate hanging out for the ride. That phenolate sees that ester so close, and it says, not so fast, buddy. And if you look at the front page of your handout, look at the lamellarin structure. Do you see it? Front page of the handout? Can you map lamellarin onto what I just drew here? Great. Okay. Well, annulative methods to make these types of things are widespread in the literature. And so that's why we have problem of the day number 5. To help us go through some strategies, you can invent some of your own. You can maybe draw from something that you think might be known. But let's talk about some strategies that could be used to make this type of pyrrole ring system, which I would say is not so undrug-like. It certainly is natural product-like. And given the success of Lipitor, I'm not sure if you would be completely fired from the company by proposing something like this, as long as you're an electron withdrawing group. You may get them demoted, but if it becomes a drug, you'll be a hero. Problem to number 5. Who is going to help us with this? We have Saul has vigorously volunteered, not just volunteered.
So vigorous. Since we have first there's intermediate, we can just brominate that immediately, then aerolate. So I'm disconnecting both the NC bond, it's exocyclic, and the C2 position.
So it's going to be easier if I can label this for all of your disconnections. So tell me what bond you want to break.
The N1 to C6, and it's going to be the last, and then the C5 to the phenyl is going to be the second to last.
And on the AR is going to have something we can alkylate with.
Right.
Yes, okay. And then?
If you disconnect the C5 to AR bond, you're literally at Ferstner's intermediate that's on the bottom of the board before.
C5 to AR gives us...
Just replace that with an H.
that we saw right there. Awesome. Well, there's multiple arrows here. That must mean there are other opportunities for someone else to have a disconnection. Or Saul to give us another one. Either way, it's fine.
I'm happy to keep going.
Let's keep going. What do we got?
So if you disconnect C2 to E last, that can very easily be done from metallation. Metallation of a parole.
All right. And now how do you want to make this thing?
We're still going to have to disconnect.
You know, your simplifications are not so dramatic so far. Like, we have to go far to get to, a union between two pieces. But keep going. So how do I disconnect this thing?
I mean, still at some point, you're going to need to disconnect C1, N1 to C6, probably at a late stage. And then start getting some things.
Okay, now what do I do?
This I would probably build.
How? You're not going to get away that easily.
From 1,4 dicarbonyl.
Okay.
Just do common. And then this can easily be made from ester.
So you're going to take...
You can see the board on the screen.
that and then reduce. Any other suggestions? Saul?
We can disassemble the parole in earlier retrosynthetic disconnection, potentially. Right? Like, basically annulate the parole on.
Yeah, let's talk about annulating the parole. What kind of bonds would you break for a annulating the parole type strategy?
So probably you start from the tetrahydrous quinoline.
Give me some bond numbers.
Oh, sorry. Break N1, C2, and C4, C5. Let's start from the tetrahydroisoquinol alone.
And what would you append on first?
Both species N alkylation is a lot easier than O alkylation, so I'd probably append on something to make the imid.
Something like this?
Yeah.
And then find a way to annulate AR1 and AR2, perhaps with some sort of electron withdrawing group here. Like this?
Sure.
I'm not sure if that would work as drawn, but it's reasonable to think about it, just because the amide carbonyl is not that adept at accepting weak nucleophiles like you would have after the addition. So this one is a questionable one. I mean, maybe the TAs can look it up after in SciFinder. And I'm going to go with a question mark because I have my doubts about that disconnection, but it's creative. I mean, we could take some inspiration from what we saw here, and you could start imagining roots like this. I thought that's where you were going to go with this. So you can make that, and then this should be very easy to add something like that.
So do you think it would be difficult to make the bunch or get much known from that?
Sorry?
Making the bunch known from the salt minerals?
Make me a munch known. Oh, I see. That's an interesting idea. You mean this type of thing?
Yeah.
Yeah, that's a great idea. And that would just come back from that. Great. Thanks, Ben. Any other disconnections one can imagine? You know, I bet that you could do sort of the same thing we saw before with the Barton Zard. So I bet if you took this intermediate and treated it with base in the presence of AR1, AR2, and simply heated that one up, all you basically need at the end of this is some sort of oxidant. So you would need to Michael it in, and then perhaps an oxidant would help you close. So there's probably some even other ones. Oh yeah, look at that crazy one up there. So you could even imagine starting with the nitro compound, nitrone, sorry. The nitrone will do a 3+2. This is a really bizarre one. give you this type of species. And if you continue to heat this thing up, it will do something that will make you dizzy. And then this thing can open up to a very stable anion. And look what we've done now. This thing can now snap shut. And that gives you the same product as that. There's probably 10 more. We won't do them all now because you guys are going to fall asleep and we don't have a lot of time. So let's move on because we have to cover quite a bit in the next 10 minutes. So, pelode synthesis. This is completely useless in its original manifestation. How do you think this works? Max or Max?
Just condense hydrazine onto the carbonate, and then do that twice, I guess. And then just do like 3-3.
Yep. Tautomerized 3-3. Modern variant would be what? Somebody, can you invent an Orglat for me? Well, the secret is what Max just said. That's the intermediate. Aha! How do we make these things? You could start off from this. Almond, Chan-Lam, heat. You'll get the same intermediate. That's how you make the unsymmetrical ones. You can do cycloisomerization. This is taught in the next lecture, so I don't need to go through it. Thank you, Kiri. You can do hydroformylation. Again, Kiri is going to teach you how that works. And finally, as we talked about before, that Tanner helped us with, you can use butadiene and do some fancy Vacker chemistry and to get directly to the pyrrole. Okay, so in the final 10 minutes, and we should have had more time at the end, but I went too slow. It's my fault. We're going to talk about radiolabeling. It's a topic we're going to see every single lecture. We will, in almost every lecture, have a deep dive into radiolabeling. As we mentioned before at lecture 1, we've got a lot of stakeholders we need to satisfy. The med chemists, we've talked about profusely. We've talked about the process chemists. We'll talk about them all the time. But there's a subset of people, the radiolabeling. How many people does La Jolla have in radiolabeling, or are they all Groton?
I'm not aware of any.
They're probably all in Groton.
Yeah.
Every big pharma company's got them. They all need them. There's usually, like in a company like BMS, there may be 3 or 4 people for the entire company. You need them, and the way they think is totally different. So usually for the metabolism studies, you have to find this stuff in the rat urine or wherever it is, and the best way to find it is to have a radiolabeled variant that you can easily pick up by some sensitive technique. You've got two types of isotopes. The stable label, meaning the ones you can handle and you won't get cancer. And then you've got the radioactive ones that have got to be dealt with in a special lab with a special permit that you don't want to go near without a lead wall between you and the chemistry. And so the stable labels are the ones like deuterium. You guys deal with deuterium all the time. C13, there's natural abundance C13, but you can enrich it. N15, you can be enriched. The radioactive ones are tritium, C14, C11, 18F. The half-life of C14 is pretty long. That's how they do radio dating. C11 is super short. It's about 20 minutes. F18 is about 100 minutes. Tritium, I'm not sure how long tritium lasts. But, these are the ones that people will generally use when they need something to, count their their beta emitters, so that you can count count them, and it's very, very sensitive. So the key here is the ground rules for retrosynthetic analysis when you're a radiochemist is you pay no attention to the cost of anything except for your starting radio component, because these things are uber expensive. So normally when I consult for radiochemists, I always ask for what the process route is, because what I'll do is degrade a process material and then reconstitute it to get the radio-labeled product. That's usually the best way to do it, because the material is basically free. It doesn't matter if you take 10 steps, as long as step 9 is the one where you put the radiochemical step in. If you do propose a radiosynthesis where you're doing a radioactive isotope, and you do 10 steps, and you install the isotope at step 1, you'll be fired from that position. Because every time you do a step with a radio-labeled isotope, you have a huge waste stream that costs a lot of money to process. So the best radiochemists are able to make from the cheapest starting material, like KCN, CO2, D2O, KF, ammonia. Those are the starting materials they use, and they can radio-label anything. So if you want to understand how to do radio-labeling and you don't know how to do ring synthesis, and all you know how to do is ring substitution and buy things and check SciFinder, you're in big trouble. For example, let's talk about pyrols. We're going to do this with every heterocycle. How do you make that one? Radio-labeled with C14 at that position. Any quick suggestions? Tanner, any thoughts?
Start from the cyanide.
Cyanide where?
The big bond is the CO.
So get me back to what's going to be the way I make this thing. That carbon needs to be labeled. So what's my starting material?
So clip off the arrow ring first.
Pop off the arrow. All right.
The fluorinated arrow ring.
Pop off the fluorinated arrow ring first.
Like it can be done across that line.
Okay, I've still got this carbon that needs to be labeled. And so I'm really happy you made this disconnection. This is great, because you wouldn't want to do this as a radiochemist. I still need to make this thing. And now you're forcing me to do bromination. I don't even know what the regiochemistry of the bromination is. I'm going to have to run a column. I've got this stuff which is like a ticking time bomb. It's the waste produced. It's a beta emitter. It's hell. So I want to put that thing in at the latest possible minute. How would you put this together? Just this one? It's multi-step, right?
Yeah.
So the way you might want to put this thing together would just be to use 1,4-dicarbonyl logic. You get that in C2, you add in that, and you got product. And where does this thing come from, Saul? And that's labeled. This thing came from and if I look at my starting materials, I've got starting materials like DMF that I can use. Put that aldehyde there, do a stetter right away, and then in the same pot, dump in my amine. How about this guy? Hannah, any thoughts?
Which one are you talking about? This goes back to the isocyanide.
Aha! Isocyanide. Brilliant. So we're going to start with which carbon needs to be radio-labeled? A sounds good. And this one can come from DMF? Well, we learned how to make it back when Max was rolling his eyes. Remember? That's all the way back here, right?
I see. So that one comes from formaldehyde?
Yeah, so you just choose either your formaldehyde or you can make it from the formamide. So you can make either labeled version of Tosmic, which will give you either of the two isomers. And I think that for this one, it's A here. I think we screwed that up. Because that's your isocyanate. No, we had it right. Sorry. That was right. And then B is here. Great. How about this one, folks? Real quick, you can call it out. Max, you got it?
It's
With the diketone. So this one is going to come from Jesus, this construction is... Hold on. So if you put those two together, and this here is going to be radio labeled, you'll get out which can then deformulate and give you product. What was the way you were going to make it?
with the 1,4-diketone.
With the 1,4-diketone is also fine. Plus ammonia, yes. This is the way they did it, just for ease. The way they made this was using NaNO2 and the corresponding dicarbonyl. But this way is also perfect. No problem. We got that one. We got that one. We have one more one right here. Love it. 3 bromo tips. Perfect. So you take the tips pyrrole, you bromate, only goes C3, lithium halogen exchange, CO2 quench, and you're done. Perfect. And that makes us right on time for the final problem, which is the free consulting. So this one comes from Pfizer, and it's way out of our league because we haven't talked about pyridines and we haven't talked about imidazoles. And I'm going to show you the power of what we learned in lectures 1 through 3, so that even at this primitive stage of your heterocyclic knowledge, you can still solve this problem. So every time you see a fused ring, and we'll have a whole lecture on this, you need to make a decision. We've got team pyridine. Who's team pyridine? We've got Dongmin and Steve, and then we've got team imidazole, Chang and Nick. Which of the teams is more aromatic? Yeah, you guys, not that you're smelly, but that you're more aromatic. And so when you make a choice, remember what I told you when we talked about aromaticity. Aromaticity can guide retrosynthetic analysis. So if this ring is more aromatic, does it make sense to make this disconnection? Does that look good to you? Like, does it feel good to you? You haven't even learned either of these heterocycles yet, but it still doesn't feel good to you. Let's look at the opposite way. Does that feel better? Do we know how to make this already? You can buy that. You can make it from using what we learned in lecture 1 or 2 or 3, directed metallation. I mean, you can buy that, Patrick. And then the great thing about this is that you can buy all of them. You can buy or make all of them. Whatever substitution you want, you can put anything you want here, reduce that down, reductive amination, you'll get your benzylamine, throw in, we won't learn about this till another few weeks, and then throw in your formaldehyde formic acid equivalent, because that is the oxidation state of formic acid. And then you're done. How does that look? Is it okay? All right, super, guys. Well, I'm sorry, I went over by 3 minutes. We'll see you tomorrow for fun with furans. Oh, yeah. When I draw these conservative arrows, I'm agnostic as to direction. Any direction you want. Yes. You can even do it stepwise. So first you add it from nice. Yep. Yeah. How come this is? Because you can't make a carbocation. Yes. And so you have a migratory aptitude between hydride shifting and arrow shifting. And phenonium is the best. Yep. That's why the hydride doesn't go. Okay. Yep. If you got just 2 protons there, the hydride goes. Okay.
Well, now we can hear it.
Would you guys mind looking down the discussion?
Yeah.
Yeah, we need it after, too.
If you would do eraser, then I'll do that.
Okay, thank you.
This line?
Yeah.
Ooh, someone took advantage of free consulting today.
Yeah. Oh, yeah. We actually getting consulting questions
good.
every day except for now. You guys use the Apple TV? Yeah. Here.
What's that?
You guys use the Apple TV?
TV.
To project stuff on the board, or?
Yeah, I think we do, but just from the laptop, I guess. Is that the same thing?
Yeah.
Yeah.
Okay, here, so I can